Welcome back. I'm actually recording this before break, and I'm already dreading coming back from break. Welcome back. Let's start a new unit. Take a look at some of these different things that you're going to be able to do. We're looking at galaxies. This is our galaxy unit. Now, before we can jump into galaxies, let's talk about how we classify things. If we were to classify a bunch of different types of vehicles, maybe we could classify them based on how they get around. And you could have a group of vehicles that get around with wings. You could have a group with wheels. You could have a group that gets around on water. And then each group would have a number of vehicles in that group. Maybe you don't want to organize them based on how they get around. Maybe you'd rather organize them based on their size. So you could have small vehicles, medium vehicles, and large vehicles. Small vehicles could be something like a bike. A large vehicle could be a battleship. There are different ways to organize vehicles. If we were in class, we would now go over to the tables and work in groups, and we would organize a bunch of different galaxies based on photos of them. However, it's this year, and we're going to try to do this by ourselves. What I would like you guys to do is take a look at all of these galaxies. There's a link up here, and I want you to classify them. I want you to put them into groups. I want you to organize them based on whatever criteria you think would work the best. In your science journal, I'd like you to make a little chart like this. So what are you using to sort galaxies? These photos don't give you enough information to use size, so I'm going to use size as an example. Maybe you could sort galaxies based on their size. And group 1 might be small, under 10,000 light years across. Group 2 might be medium, 10,000 to 100,000 light years across. And group 3 might be large, 100,000 to a million light years across. And maybe you need more than 4 groups. Maybe you need a 4th over a million light years. Maybe you need a 5th, a billion light years. Just as a hint, there's no galaxies that big. But I don't want you to feel confined to only using 3 groups. If you need 10 groups, use 10. A lot of times if you use more groups, it's actually easier to do. Trying to categorize everything with only a few groups sometimes can get pretty tricky. I'm going to pause the video, and I want you guys to organize these galaxies based on whatever criteria you think works the best. And now I'm curious, what type of things did you guys use to categorize galaxies? Maybe you used their shape, maybe their size, maybe their color, maybe how dense the amount of stars were, maybe how bright they were, how far away they were. And in this activity, you didn't have enough information to do that. Maybe what type of stars were in each galaxy. Are they young blue stars, old red stars? Maybe they had a large central bulge, which is where all the stars are gathered up in the center. I wonder if astronomers could use whether or not galaxies are coming towards us or away from us. In past years, when I've done this, different groups have organized them based on a bunch of different criteria, and none of them are wrong, because there are a lot of different ways to organize things. And I say that so that we can now look at how astronomers organize galaxies. It's all based on the work of Edwin Hubble, who back in the 1920s was studying galaxies. He did things other than that. In fact, he also figured out that the universe is expanding, and that's probably what he was most famous for. But he came up with this tuning fork method of galaxy evolution. According to Hubble, you would actually start out as an elliptical galaxy, and you would end, as billions of years later, a spiral galaxy. And we now know that that is not necessarily true, but let's take a look at what Hubble said. Here's his tuning fork, and he has E0 would be the youngest. And you'd go out to E1, E2, E3 as time is going on. And you notice that as time is going on, these elliptical galaxies are starting to kind of smush. Until eventually, you get spiral galaxies, and you have spiral A, spiral B, spiral C, and you can tell that you get more and more spiral arms as time goes on. The other prong of the tuning fork is what is known as a barred spiral, because there seems to be a bar going through the center bulge of the galaxy. And as time goes on, that bar is going to extend and get skinnier. So you can see that his tuning fork started as an elliptical galaxy, and as time moves on, you end up as either a spiral galaxy with a lot of arms or a barred spiral galaxy that is very elongated and kind of skinny. That's what Edwin Hubble thought was happening. But he was wrong. Why would I even tell you what he came up with if he was wrong? The reason is that we still use those names. We still use elliptical galaxies, we use barred spiral galaxies, and spiral galaxies. So, you're going to want to write these down. The types of galaxies: we have a spiral galaxy, we have an elliptical galaxy, and we have what is known as an irregular galaxy. So, spiral and barred spirals are both in this first category. And now we have irregular, which is not an ellipse, it's just a weird shape. And I'll show you some examples of those. Let's go through each one. Spiral galaxies are the famous ones. These are the ones that are on the covers of astronomy textbooks. We live in a spiral galaxy. This is a photo of what's known as the pinwheel galaxy. It's one of the most photogenic galaxies out there. It is on the other side of our local group. Most spiral galaxies have a bar that goes through the center. We actually think that our Milky Way galaxy has a bar that goes through the center. So we think that we live in what's known as a barred spiral galaxy. These galaxies are very flat, very, very flat. Our galaxy is about 100,000 light years across and only about 1,000 light years tall. That would be similar to having a disk that's about 8.5 feet across and only 1 inch tall. So it's very, very, very flat. These are very flattened structures. And they have spiral arms, hence where the name comes from. If you look at one of these edge on, you will notice that the center bulges out. The vast majority of stars in a spiral galaxy are at the center, because that's where the most gravity is, so they are being held close to the center. If you are looking at them, the brightest point is going to be at the center, where you have the most stars. If you look over my head, you can tell that the brightest point of that galaxy is the center. That's what's known as the central bulb, because it bulges out. Here's a perfect example of a barred spiral galaxy. You can see that it is a spiral because it's got spiral arms, but there is a bar that seems to go through the center. Our Milky Way has a number of spiral arms, but we also know that it has a bar. How do we know that? Well, we don't have a photo of it, because in order to take a photo of a galaxy, you have to be outside of the galaxy. And if our galaxy is 1,000 light years tall, well, our fastest spacecraft, it would take millions of years to get outside of our galaxy. Needless to say, we have not been sending things up to space for millions of years. So how do we know this? The reason is that we can look out and see stars, and we can plot how far away they are, how many there are in each direction, and we've been able to kind of plot out a 3D map of our galaxy. We are in a spiral arm, about halfway out from the center to the edge, and towards the center of the galaxy, we have a bar. Spiral galaxies are the most common, and as a hint, they're also the youngest. I want you to notice what color this is. Kind of got a bluish tint out in the arms. It's got a yellowish tint closer in. Well, that tells us that there are a lot of young blue stars out here, and there's a lot less of them in the center, which means the stars in the center that were blue have died out. The oldest part of these galaxies are in the center, and the arms are where you get young new stars forming. And you can tell all of that information just by looking at the color. The bluer it is, the younger it is. If it was very red, that would be a very old galaxy. So to repeat, if you notice the arms, they are very blue, which tells you there's a lot of O and B class stars, those very hot ones. And we also know that those blue ones live a very short amount of time. And because those O stars have a short lifespan, these blue stars out in the outer arms are very, very young. They just formed on a galactic timescale. If stars are forming in the arms, how do they get in between the arms? Or how do they get towards the center? Well, it turns out that these arms are not permanent structures. The galaxy is actually spinning. And if you look closely at this computer model, at any particular point, these arms kind of disintegrate and then reform, and then disintegrate and reform. And I want you to just focus on a point in any of those spiral arms to see whether or not they really do in fact orbit as an intact structure. And they don't. So the spiral arms of galaxies, they actually just disintegrate and then reform, and disintegrate and reform. They don't stay as a spiral arm. So while new stars are forming in these arms, they will over time just kind of spread out through the whole galaxy. The second type of galaxy that we now have is what's known as an elliptical galaxy. Basically just kind of circular. It's like a ball of stars up in space. There's not a whole lot of gas and dust, which tells us there's not a lot of star formation. How do we know that? Look at the color. Where are the blue stars? There's not a lot of young stars, which means there's not a lot of new star formation going on. And we don't see a lot of this nebula of gas and dust in these elliptical galaxies. They've already used up all of their star forming material, and so the only stars that are left are the stars that last a very long time. So just looking at the color, you can tell whether or not a galaxy is young or old. If we go back to Hubble, Hubble said that elliptical galaxies are how you start. A baby galaxy would be elliptical, and a spiral galaxy is how you end. So the oldest of the old galaxies would have a lot of these arms. Turns out he was exactly backwards. The younger galaxies are going to have a lot of these arms, and as time goes on, they just kind of coalesce into a big blob, a big sphere of old stars. So you start out as a spiral galaxy, and you end as an elliptical galaxy. So he still used the same terminology, but he had the timeline different. He had it backwards. And now we have the irregular galaxies. This is known as the bird galaxy because it looks like a hummingbird. Irregular galaxies don't have a shape. They're just like a big mess of stars up in the sky. So they're not a nice, pretty spiral. They're not elliptical like a circle or a sphere. They're just a mess. And we think that they happen when two galaxies actually merge, and the gravity of one galaxy tears apart the gravity of another galaxy. And now I want to see if you guys can identify any of these. What type of galaxy is this? I'll give you the first one for free. This galaxy is kind of circular, does not have a lot of blue stars. This is going to be an elliptical galaxy. What type of galaxy is this? Spiral. What type of galaxy is this? A barred spiral. What type of galaxy is this? An irregular galaxy. What type of galaxy is this? Another spiral. What type of galaxy is this one? A barred spiral. What about this one? This one is irregular. It's just kind of a random shape. Hopefully this one's not too hard. An elliptical galaxy. Galaxy number 9. This one is a barred spiral. And this one, spiral galaxy. Hopefully none of those were too difficult, especially after I told you the answers. If classifying galaxies seems kind of easy for you, and you want to help out actual astronomers, well, there are hundreds of millions of galaxies out there that astronomers need to organize and classify. You can actually go to galaxyzoo.org, and it will show you a picture of a galaxy, and you can click. This one is a spiral galaxy. This one is a barred spiral. This one is irregular. Sometimes when I'm bored, I randomly just go there and start clicking through and organizing random galaxies to help out some astronomer that I don't even know. I say give it a shot. There's a link. And finally, where do galaxies come from? How do they form?
Most things in the universe happen too slowly for us to see them happening. Stars like the sun take tens of millions of years to form, and hundreds of millions of years to orbit their galaxies. And colliding galaxies take billions of years to merge. And yet we have a pretty decent understanding of how all these things happen, because there are so many of them in the observable universe that we can look out and see different versions of similar events happening in different places. And because light takes time to get here, we see places at different distances at different times throughout the history of the universe. And from all that, that, we can piece together an understanding of how stars are born and how they die, how galaxies develop and interact, and so on. It's kind of like if you only had 10 minutes to study how humans grow, you couldn't see any one person grow very much in that time. But by looking at humans of different ages all around the world, you can get a pretty good picture of what a human life looks like. However, the very first galaxies to ever form were so small and dim that we don't have nearly as good an idea of how baby galaxies are born as we do about how they behave and interact later in life. Our current understanding is that in the early universe, before any stars had formed, everything was just spread out gas and a lot of dark matter. Dark matter is matter that doesn't interact with things other than by gravity, so we call it dark because we can't see it. Gravity would have caused slightly denser areas of dark matter to attract into clumps, pulling in bits of gas until they were dense enough on their own to gravitationally collapse and start thermonuclear fusion. A star. Many stars. Clusters of stars and their associated dark matter attracted together and merged, and then those clustered clusters clustered together, eventually forming the most distant and longest ago galaxies we see today. But we don't know exactly how soon after the Big Bang the clumps of dark matter and gas formed, or when during the process of clumping and clustering the first stars ignited, or if there was a minimum dark matter clump size necessary to attract enough gas to form stars, or if the very first star clusters came together to form galaxies at all. They might have been so small and fragile they were blown apart when their own stars went supernova, and the first galaxies may have actually formed from a second round of clumping of gas and dark matter as well as dust from the explosions. To be honest, we don't even have a good enough definition of what a galaxy is to know when to stop calling something a cluster of stars and when to start calling it a galaxy. What we do know is that today we have bajillions of galaxies in our universe, none of which existed 13.8 billion years ago, so somewhere in between, they must have all been babies. Big, gassy babies surrounded by clumps of dark matter.
Now it's time to practice.